our goal for today is to delve a little deeper into acceleration. Now, we understand we have our velocity, which is explaining how are we moving right now, but acceleration is how is that changing? And in particular, we could say, look, if we're moving in this way, our acceleration might be pulling us to one side so that it causes us to turn. So in essence, the acceleration is really split into two parts. One part goes with velocity, one part goes perpendicular to velocity. That's sort of the pulling it to the side part. So what we want to do is say, hey, let's take acceleration and break it into these two parts, with and perpendicular to velocity. That's where we're going. Let's begin. So we want to start by talking about something called the unit tangent vector. Now, you kind of have an idea of what it is. So first off, it's tangent, so it should be touching the curve. In other words, it should be mimicking what the curve does. The word unit tells us it should be length 1. So we know that r prime of t, that's the direction of the curve. So in essence, it's the direction of that tangent line. So we can think of it as the vector which is mimicking the curve locally. By dividing it by its magnitude, we get a unit vector. So we say, look, this tangent vector, this unit tangent vector, perfectly captures motion. In fact, we can say the following. Our velocity can be written as a product of the magnitude of r prime of t with the direction. This goes back to the idea that every vector really has two parts. One part is its magnitude, or if you like, its length, and the other part is its direction. And so all we're saying is we can decompose it into its two pieces, magnitude and direction. Put them together, we have our vector. So now we have our velocity, and our goal is we want to understand acceleration. So let's take a derivative. So our acceleration, which is the derivative of velocity, okay, so now it's the derivative of two things. They're both functions of t. We have this magnitude of r prime of t, which is a scalar function. In other words, the output is a number. And we have this t of t, and that's a vector valued function. Its output is a vector. But we can still think of it as two things multiplying together. And we still have the product rule. So it's the derivative of the first times the second plus the first times the derivative of the second. Now there's a claim here. Well, one thing is this is parallel to motion. Well, yeah, it has to be, right? Because look at the direction. The direction is the tangent vector. So if the direction is the tangent vector, and the tangent vector is the direction of motion, then if I'm scaling it by this quantity, then it has to be parallel to motion. Because anytime I scale a vector, it's still parallel to what I started with. The more subtle part is the second term, right? The magnitude of r prime times the derivative of our tangent vector. We say, look, that's perpendicular to motion. Now that one is a little bit more subtle and maybe not so obvious unless you go back a few sessions and we said, hey, there's this really cool fact that says that if you travel on like a sphere, then your direction of motion is perpendicular to where you are. In other words, the function is perpendicular to its derivative. Well, notice that the unit tangent vector has length 1. See, that's what we're saying here, length 1. And therefore, by that fun property, we say, aha, the derivative is perpendicular to the function itself. Fantastic. So we know that this vector valued function, whatever it is, has to be perpendicular to our tangent vector. That's why we know it's perpendicular to motion. All right. Well, so it's pointing in some direction that's perpendicular. And if we have something perpendicular, we like to call it normal. Think like normal vector for a plane. Perpendicular to the plane, normal vector to this curve, it's perpendicular to the curve. So we say, all right, so we've now written acceleration as one part parallel to motion and one part perpendicular to motion. Perfect. We've been able to decompose, break it into parts. And so we're going to be a little bit more precise. Say, look, there's really this little thing called a sub t, and that says how much of acceleration, the quantity of acceleration, points in the direction of motion. And then there's this other function, a sub n. How much of the acceleration, the perpendicular part, points in the direction of, the acceleration, how much of it points perpendicular to motion. So these are scalar functions, and then these are vector valued functions, the unit tangent vector, which is what we've already talked about, and the unit normal vector, which is the one we just discovered. Now, be careful here. We are not saying that this derivative is exactly n of t, because we don't know what the magnitude of this vector is. We only know it's perpendicular to what we want. So there's this scaling that goes on. So there's a little bit of subtlety in play. So our goal for today is to delve a little bit into saying, how do we actually go about computing some of these things, like a sub t and a sub n? The unit tangent vector, okay, easy enough, that's fine. What about things like n? What would we do there? What's the right way to do it? So we're going to do it in essentially two different ways. One is using geometry, and one is using algebra. Let's start with geometry. All right, so now we have a picture, and it's always nice to have a picture. So what's going on? We have our curve. Here we have r of t. So we have our particle traveling along our curve. And here's our particle at a given time. So r prime of t points in the direction of the motion, and then r double prime of t points in the direction of acceleration. All right, and you'll notice how our curve is turning and the acceleration is sort of pulling it to the side. That's what acceleration can do. It can help us turn directions. Now, that's assuming, of course, there's a significant amount of acceleration that's perpendicular. If acceleration is mainly pointing in the direction of motion, it's sort of speeding us forward in the direction that we're currently going. And now, here's sort of the idea. Think about this triangle that you see here. See, I can really break this up into pieces. So I have a little piece down here, and then I have a piece down there, right? So what I have is this part, that's how much of acceleration points in the direction of motion. And that part, that's how much of acceleration points in the direction normal to motion. And you can see if you put them together, this plus that gets us to acceleration. And of course, it's not just any kind of triangle. It's the right kind of triangle. So we say, look at this triangle. What do you have? Well, the hypotenuse, that's the magnitude of your second derivative, or if you like, the magnitude of acceleration. Our adjacent side, that's how large our portion going in the direction of acceleration is. But remember, the amount, the size, that will be a sub t. A sub n, that's this side, how much is going perpendicular to motion. Now, we pretty much are like 95% there, right? Because we say, we have a triangle, and we say, all right, suppose I want to find a sub t. Well, that's the adjacent side versus the hypotenuse, which we know. So cosine, that's the adjacent over the hypotenuse. So if you just rearrange, we can say, aha, a sub t, magnitude of r double prime, cosine theta. And we say, boy, that sounds really familiar. It's almost like the dot product, right? Except the dot product has a little bit extra. So if you added in the magnitude of r prime, and we can do it by putting in both top and bottom, we say, aha, that's the dot product upstairs, magnitude of r prime goes downstairs. So r prime dot r double prime divided by the magnitude of r prime. All right, that's a sub t. Now, on a side note, you might say, this is sounding really familiar, like really, really familiar, insofar as it feels like projection. And that's because it's projection. You can think of what's happening is you can say, hey, this is really the projection of the acceleration, r double prime of t, onto r prime of t. Except instead of looking at the vector, we just say, look, all I care about is the magnitude, the scaling factor. One other side note I want to point out here, and it'll come into play in just a second, but that is that a sub t can be positive or negative. And that's perfectly fine. Now, what does it mean if it's positive? What does it mean if it's negative? Well, essentially, if we think about just one-dimensional, so if a sub t is positive, if I have a particle moving and acceleration is in the same direction, what will happen is that the particle will start to speed up. It's going faster. If acceleration is in the opposite direction, that means the particle's slowing down. So it's okay to have positive or a negative value. Both can be interpreted appropriately. So keep that in mind, because we're going to come to a sub n, and we're going to point something out here in a second. All right, what is a sub n? Well, look at the triangle. It's the opposite side, right? So we say, hey, that's sine. So sine of theta is a sub n over the magnitude of r double prime. Well, all right, so a sub n magnitude of r double prime sine theta. And then we're like, there's fact about sine that we recall. Something seems to cross our mind. Cross product. So if we multiply by the magnitude of r prime, we say, aha, this is still the same because the magnitude of r primes cancel, but the numerator is now the magnitude of the cross product. And so we get magnitude over magnitude. Now, notice a magnitude is something which is greater than or equal to 0. So that says, look, a sub n is always greater than or equal to 0. It's never negative. This will be useful in something we're about to observe in a second. So now we put it all together, and we say, well, I know how to find a sub t, I know how to find a sub n, so I can break apart acceleration. So remember, acceleration is just another way of saying r double prime. So it's r prime dot r double prime over the magnitude of r prime times t. This is the projection, and then this is the other part. And in some sense you're like, oh yeah, it kind of makes sense, because what am I looking for? I'm looking for something which is somehow perpendicular here. I want it to be perpendicular to the motion. So r prime crossed r double prime, that should be something which is perpendicular. So good. All right. Now, this can be wonderful. And when we do some examples, we'll definitely do some examples where we do things in a nice geometrical way. In some cases, it can be challenging because you have to say, I've got to find r prime and r double prime. You got to do that anyways, because if you're looking for acceleration, you got to be able to talk about acceleration. But what can be hard about this is, well, you have to take a cross product, you have to take dot products, you have to take magnitudes. It can get a little bit iffy if you're not careful with your computations. And if your function is terrible, it can get really, really messy. So all this is to say, as a word of warning, most people tend to lean towards the next method to do it. And there's some very strong reasons to use the algebraic approach. That being said, I think it's good to know both. So I want to point out one advantage that this has, and it'll become more clear what I mean as we go forward. But so what's the advantage? Well, this has a strong advantage if you're looking for decomposition at a specific time. In other words, saying, look, you can talk about decomposition at any time, and you can think of those as a function of t. But you can also say, look, I just really want to know what happens at time 1 or time 5 or whatever, it doesn't matter. If you're looking for a specific time, then this actually has an edge. And the reasoning behind it is to say, hey, you don't actually have to, do lots of massive computations with these vectors as functions. You take r prime, you take r double prime, you evaluate and then you do all this cross product and magnitude, and then life becomes a lot easier. So there is a good case to be made to know both, not just the algebraic. Okay, so we've talked about geometric. Let's do the algebraic. So here, it's actually pretty straightforward. It says, wait a second, we already know how to find a sub t. That's a freebie. And you might say, well, how do we know that? Okay, so let's go back a couple of pages here. Let's see if we can find it. When we said, look, we can write our acceleration here, right here. See, acceleration, it's the derivative of r prime times our tangent. We said, okay, that's a sub t times t. Well, look, since that matches, that has to match. So our derivative of the magnitude of r prime is a sub t. Perfect. Okay, so that says, look, step 1, find the magnitude of r prime. All right, that's easy enough. So, okay, so step 1, find your magnitude of r prime. Step 2, find a sub t. That's the derivative with respect to t of the magnitude of r prime, what you just found. This, of course, works best if the magnitude of r prime is nice. You'll see that many of the curves that we consider, magnitude of r prime turns out to be suspiciously nice. Now that gets us halfway. What's the other half? Well, we need a sub n. Now at this point, like, ha ha ha, now you're stuck. Ah, let's go back. There's something we can take advantage of. You see, we talked about this triangle here. And we said, look, it's not just any triangle. It's the right kind of triangle. And then we went into trigonometry. We talked about the ratios, sine and cosine. But there's some other beautiful fact about right triangles, which is the Pythagorean theorem. So, by the Pythagorean theorem, we have a little side note here, which says if we add up the squares of the sides, so a sub t squared plus a sub n squared is the magnitude of acceleration squared. See, that's our hypotenuse. So these are the other legs. And so now, step 3 says, look, perfect. I can now solve for an. So a sub n is equal to the square root of, you take the magnitude of acceleration squared, subtract what you just found, squared. And you're done. Now you might say, whoa, wait, how do you know it's the positive and not the negative? That goes back to what we talked about. A sub n is always going to be greater than or equal to 0. So we always are going to take the positive one. So that's it. It's actually pretty straightforward. Find the magnitude of r prime, take its derivative, find the magnitude of acceleration, and of course we really could have written this as the magnitude of r double prime, squared minus a sub t squared we just found, take the square root, you're done. And that's it. Now, what's great about this? Well, one of the things that's great about this is it works in any dimension that you want. You see, when we did it geometrically, we said, we had a cross product. Now, cross product is wonderful, but there's one small catch whenever you use a cross product. You have to be in dimension 3. That's the only dimension where cross product makes any sense. This says, look, you can be in 5, 7, 122, 2, any dimension at all, and this process will help you find out what's going on. So there's a definite plus to this method. And computationally, most of the time, I will say in most problems, this is the faster way to do things. But like I say, know both. Now, the last side note here. We've talked about a few vectors. We've talked about the unit tangent vector. That's pretty straightforward. R prime over the magnitude of r prime. Now, the unit normal, that's messy. And because, the unit tangent vector tends to not be nice to begin with. Once you start taking derivatives and taking magnitudes of those, it gets even worse. What's a better way to figure this out? Well, in essence, what you can do is, and this is just my own opinion, so one way you can solve for your normal is to say, look, I can do the following. I can take my r double prime, which is acceleration, subtract at times t. In other words, take r double prime and subtract the projection. Now, this is the right direction for the normal, and therefore just divide by the magnitude. That's probably the fastest way to actually find the unit normal vector. There's also something called the binormal vector. What's that? Well, it's the cross product of the tangent and the normal. Well, hold on. Wait, first off, how do we know it's a unit vector? Well, because these two vectors are both unit vectors and they're at a 90-degree angle. If you go back to the magnitude of a cross product, it's the magnitude of the first times the magnitude of the second times the sine of the angle. 1 times 1 times 1 is 1. Okay, so that's why we know it's a unit. What does this vector have? Well, it has the motion, because that's the tangent. It also has this direction perpendicular to motion, which is the acceleration. But see, acceleration is a combination of both the tangent vector and this normal vector, which means it has motion and acceleration, and therefore it's perpendicular to both motion and acceleration, which means it's the normal vector to the osculating plane. Now, probably the worst way to compute the vector b of t is to actually say, okay, I'm going to find t, and then I'm going to find n, and then I'm going to take that cross product, and then I'm going to be like, I'm done, and this is great. Because by the time you get there, you'll be like, why? Why have you done this to us? Because it's a lot of work. There's a much, much faster way. We say, hey, look, we know what it is. It's the normal vector to the osculating plane. So we say, okay, well, look, find the vector to the osculating plane, which is done by taking motion cross acceleration. That's the osculating plane normal vector, or that's a osculating plane normal vector. Only challenge is it may not be perpendicular. Easy to fix. Sorry, it is perpendicular. It may not be unit. Easy to fix. Divide by its magnitude. That's a much, much easier way to go about finding the binormal vector. All right, so there we go. That's our decomposing acceleration. Two different methods, geometry and algebra. Be ready to do both. And we will do both on some of the examples just to say, aha, see, it works. It's not just a theory. It works in practice. Of course, that means we've got to actually go and do practice. So I'll see you in a practice session soon. Bye.